Welcome back to linear algebra. In this video, I want to look at using an orthonormal basis. Those are words that you are familiar with, but the combination is slightly new here. We know that a basis is a very powerful tool for describing a set of vectors, a vector space. And we know that having an orthonormal set gives us some nice properties about the vectors we're dealing with. Combining those two ideas is a little bit strange, however. But as I alluded to at the end of the last video, if we take our standard unit vectors, or our standard unit vectors of the Euclidean n space, they will form an orthonormal set and give us this idea of an orthonormal basis. So we are once again trying to take that idea from the Euclidean space and allow us to extend it to other vector spaces. So without further ado, let me get my head out of the way. Let V be an inner product space, and let S be the set of vectors u1, u2 through to un, which is an orthogonal set full of non-zero vectors. So all of the vectors in S are orthogonal to each other. Their inner product is 0, and the vectors themselves are not 0. With those two claims, we can conclude that S is going to be linearly independent. I do want to point out before I dive in, it makes sense that I have to specify here non-zero. It's what I talked about in a previous video, where having the 0 vector count as orthogonal or not, sometimes it's useful, sometimes it isn't. But the 0 vector is not linearly independent to anything. If the 0 vector is inside a set of vectors, the set is not linearly independent. So it is important that we make sure that the 0 vector does not show up here. And we'll start off the same way we often do with proofs of linear independence. We're going to pick a bunch of constants so that the linear combination k1u1 plus k2u2 down to kn is equal to 0. In order for this set of vectors to be linearly independent, it must be the case that the only constants that will satisfy this are k1 through kn all 0. I think it's obvious that if k1 through kn are all 0, then this equation is satisfied. So what we have to show is it's impossible for k1 through kn to be anything else. So I'm going to pick I somewhere between 1 and n, and I'm going to take the inner product of this whole left-hand side with ui. And now we know that the inner product of the 0 vector and anything else is always going to be equal to 0. And we know, thanks to homogeneity and additivity, that we can split this inner product up and we know that all of the u's are orthogonal to each other, but they're also non-zero. So because they are orthogonal to each other, as long as you picked a different pair of vectors, the inner product is going to be 0. But somewhere in here, we picked the inner product of a vector with itself. So the only term that's left in all of these inner products is the one that is ui with ui. Because ui is non-zero, this has to be a non-zero number. And the 0 product rule says if we multiply two things together and get 0, one of them has to be 0. And since ui is not 0, that means that the inner product of ui with ui is not 0. And so by the 0 product rule, that means that ki is 0. And we do this for each I between 1 and n. That wasn't my highlighter at all. That's my highlighter. We do this for each I between 1 and n, and we see that the only possibility is that for each I between 1 and n, ki is 0. And that is exactly what it takes to be linearly independent. All right, that's an interesting result, I suppose. Doesn't quite seem all that applicable to anything. Let V be any n-dimensional inner product space and take a set of n vectors which are all orthogonal. And with that, this set of vectors will form a basis for V. And as we talked about in the previous video, if you divide each of those vectors by their magnitude, you get not just an orthogonal set, but an orthonormal set. And so an orthonormal set which forms a basis for V is called an orthonormal basis. And an orthonormal basis is incredibly useful because it gives us a couple of really nice, easy things to do. So let's take an orthonormal basis. And let's take any vector V. We know that for any basis, we can write any vector in the vector space as a linear combination of those basis vectors. The reason that an orthonormal basis is so valuable is that it is very simple to figure out what the coefficients of that linear combination are. They are simply the inner product of that vector with each of the vectors in the basis. And to prove that this is going to be the case, let's start off with just that. Right? Since S forms a basis, we know that there are some constants, K1 through Kn, so that V can be written as a linear combination of all of these U's. Now, for I, something between 1 and n, I am going to take the inner product of V and Ui. All right, so that's the inner product of that linear combination, K1U1 plus K2U2 plus dot 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 plus KNUN with UI. And similar to what we did before, we can split up this inner product. And similar to what we did before, since S is orthogonal, it must be the case that all of these things come out to be 0, except somewhere in the middle. Somewhere in the middle, we are going to have UI with itself. Again, because it forms a basis, it must be linearly independent. And so it can't include the 0 vector. So the inner product of UI with itself is the only thing that is non-zero. Furthermore, the inner product of UI with itself is UI squared. And because this is a normalized set, that means that all of these norms are 1. So that's how I get that Ki is the inner product of V dot UI. And we can do this for each I between 1 and n. And by substitution, that will get us to the equation that we started with. Our vector V is just that sequence of inner products. So I've hinted at, I'm not going to explore because it's fairly straightforward. The standard unit vectors in the Euclidean n space will form an orthonormal basis for that vector space. I want to explore the orthonormal basis for a different vector space. The other inner product space that we've been discussing. Polynomials of degree n with the inner product of f and g defined as the integral from -1 to 1 of f of x, g of x, dx. And a set called the Legendre polynomials. L1 is 1, L2 is x, L3 is 1/2 times 3x squared minus 1. Oh. Numbering backwards. The Legendre polynomials show up in a number of different applications. For the sake of time, I'm not going to go through how to derive them, but I like to mention them as one of the several different places they show up is that they do form an orthonormal basis for my polynomials of degree n. For any n, just make sure that you get enough of the Legendre polynomials, and you are, in fact, good to go. Try to integrate any of these with itself. You'll get a non-zero number because they are all non-zero polynomials. But if you try to mix any two of them, you will get something that comes out at 0. And I encourage you to do that. I encourage you to take the time to play around with the Legendre polynomials, perform some integration, and verify for yourself that they are, in fact, normal and orthogonal to each other. And with that, I'm going to end our discussion here. Thank you, as always, for joining me. See what you can do playing around with some of the problems related to this, and I'll see you in the next video.